Hi, we'll be talking about attitude determination and control system. But attitude? What does it really mean? Think about an airplane flying through the sky. Its attitude isn't about its confidence or behavior, but about its orientation, whether its nose is pointing up, down, or to the side. In the same way, when we talk about satellites, attitude refers to their exact orientation in space relative to Earth or the stars. Hi, I am Rishabh and I am here with my colleague Sriza. Today we'll be sharing our work on Software Library for Attitude Determination and Control Systems or ADCS. We started this open source project to make ADCS utilities and algorithms more accessible to everyone. Sriza then used this library to implement an attitude determination algorithm, demonstrating what it can achieve in practice. Imagine the Hubble Space Telescope quietly orbiting the Earth. One day, astronomers discover an intriguing star they want to study in detail. They send a command for satellite to capture its image. But there is a problem. The satellite is not pointing at the star. It's facing somewhere else in the vastness of space. So, what happens next? First, the satellite needs to figure out exactly how it is oriented right now. Then, it needs to know where it should be pointing to see that star. Finally, it has to rotate itself so that it aligns perfectly with the desired direction. This entire process is managed by ADCS, the Attitude Determination and Control System. In simple words, the attitude determination is like the satellite asking, where am I looking right now? And attitude controller is deciding, okay, now let me turn and look exactly where I need to. Having introduced ADCS, let's talk about why open source software is important in this field. Research areas like ADCS are not accessible to everyone. Often, theoretical scientists develop ideas and algorithms, but actual implementation and validation are done by companies, large research institutes, or well-funded labs. This process often requires long R&D efforts, expert teams, and specialized equipments like hardware-in-the-loop setups, attitude simulators, and high-fidelity sensors to test these algorithms. Because of this, the software and tools they develop are rarely shared publicly. I started working on ADCS about 4 years ago, beginning with my bachelor's thesis. And as I continued exploring the field, I realized there was a significant gap. That is, there was not an open source software that students, hobbyists, or even researchers could use to play with these algorithms. That's why we created this software to make ADCS utilities and algorithms accessible to everyone who wants to understand, implement, and test them, bridging the gap between theory and practical application. Furthermore, the idea is to make software well adapted to the embedded hardware where the ADCS is implemented. In this presentation, I like to share where the project currently stands and what we have achieved so far. We use numbers to represent physical parameters in our daily lives. For example, a mass of 1 kg or a road that is 2 kilometers long. In the same way, to be able to work with attitude in ADCS, we need to parameterize it using numbers. Wheeler angles describe orientation using three angles, often called roll, pitch, and yaw. They are intuitive and easy to visualize, but can suffer from issues like gimbal lock, or mathematically speaking, singularity. Direction cosine matrices, also called rotation matrices, these are 3 by 3 matrices that can transform vector from one coordinate frame to the other. They are precise and mathematically elegant because the rotations can be performed using simple matrix vector multiplication, and consecutive rotations becomes just matrix multiplications. However, they require maintaining 9 elements with strict orthogonality constraints. Quaternions uses 4 numbers to represent orientation without the singularity problems of the Wheeler angles. They are compact, fast to compute, and widely used in spacecraft attitude control. However, these four numbers are not completely independent. They must satisfy a unit norm constraint. In other words, an arbitrary collection of four numbers does not represent rotation unless their norm is 1. Our software offers functions to handle these parameterizations and converts between them, and essential for any ADCS work. But working with orientation comes with subtleties. For example, computing error is crucial in ADCS to determine how far the satellite is from its desired orientation. With parameter like temperature, computing error is just doing subtraction. But our but for our orientations, direct subtractions does not work. Subtracting two rotation matrices break their orthogonality, and subtracting two quaternions violates their unit norm constraint. Instead, in ADCS, error is defined as the angular rotation needed to go from current orientation to the desired one. This avoids above mentioned issues, and our implementation is based on the method described by Markley and Crassidis. Another example is computing the average of two orientations. In ADCS, you might have two orientation estimates from different subsystems and want their average for better estimate. However, simply averaging their numbers produces an invalid orientation. Special algorithms developed by Markley and his colleagues allows us to compute a proper weighted average of the quaternions, and we have implemented this in the software. Finally, low-pass filtering. Low-pass filtering is an indispensable tool in engineering, including ADCS, which is used to smooth noisy data. However, standard low-pass filters assume that the data is real valued. For quaternions, we need a different approach due to their unit norm constraint. In our library, SLERP, SLERP, spherical linear interpolation, is used to keep smoothing while keeping quaternions valid. These are some of the interesting challenges when handling orientation parameters. Most of our work so far has focused on quaternions as they are widely used in the space industry. However, we also plan to implement tasks like orthogonalizing a matrix to its nearest valid rotation matrix, similar to normalizing quaternions for unit norm. To appreciate coordinate frames in ADCS, think about measurement itself. For example, to talk about mass, we need to know what the standard 1 kg is to make the comparison. Similarly, in ADCS, orientation is described with respect to something. This is done by fixing a 3-axis coordinate frame on the object which rotates and the other standard frame with respect to which the orientation is measured. The standard frame could be fixed to Earth, for example. The choice of coordinate frame can simplify mathematical computations. Therefore, different frames are used in different scenarios. Orbital mechanics often uses perifocal frame, while magnetic field calculation uses local vertical, horizontal frames. Our code base allows conversions between various frames like ECI, ECEF, geocentric, and geodetic, which frequently appear in ADCS tasks. Time is equally important in ADCS. For example, if someone says, my satellite is this latitude and longitude, this statement does not mean anything unless they also specify when it was there. In orbital mechanics, both the satellite's motion and the Earth's rotation are precisely calculated and monitored. So this time must be standardized to avoid ambiguity. For instance, Julius date represents the number of fractional days that have passed since the noon of January 1, 4713 BCE in the Julian calendar. It provides a continuous and unambiguous time scale used in astronomy and orbital calculations. There are other time standards as well, such as sidereal time, which is based on Earth's rotation relative to distant stars rather than the Sun, and Greenwich sidereal time, which is used to relate Earth fixed and inertial frames. We also have UTC, which is the basis for civilian timekeeping. Having functions to convert between these different time standards is very helpful in ADCS. And right now, our software includes support for Julian date, Greenwich sidereal time, sidereal hours, and sidereal degrees. Many ADCS algorithms require the knowledge of satellite's current location. For example, to calculate the sun's direction or Earth's magnetic field for attitude determination, the satellite must know exactly where it is relative to the Earth. Ground stations periodically send the position and velocity of satellite as initial condition to the orbit propagator implemented on board the satellite. The position and velocity are tracked using radar and telescopes from the Earth. The initial conditions can also be provided by onboard GPS if the GPS is present. Between these velocity and position updates, the satellite uses an orbit propagator to predict its future position. One widely used model is SGP4. It uses two line elements which are published orbital data to calculate where the satellite will be at any given time. It considers the factors like Earth's shape, atmospheric drag, etc. We have implemented SGP4 based orbit propagator in our library. It is based on works by Vallado. At present, we are focusing on understanding and implementing various environmental models used in ADCS. This includes exploring the mathematical models for Earth's gravity, magnetic field, and sun vector. Such algorithm uses large number of coefficients. One interesting aspect in our research is learning how to adjust or clip the number of coefficients used in these models based on the required accuracy. This allows us to balance the computational load with precision, which is crucial for onboard implementation. To wrap up, I like to say that this work is far from complete. It's a project we intend to maintain and grow over coming years. Please feel free to reach out if you are interested in contributing, or simply send a pull request if you make any improvements. Thank you.
Imagine you are playing a game where a friend blindfolds you and takes you to a new, unfamiliar place. It is now your task to orient yourself towards the west as you open your blindfold. As humans, we have clever ways of doing this. We might look up at the sun and guess the direction it's moving. Or, like ancient sailors, we could find familiar constellation in the sky and use them to determine where west is. You can also look at the compass, which, based on magnetic field of the Earth, allows you to know west. Satellites lost in the cold vastness of space also face the question of where they are looking. The challenge is termed as attitude determination, and what we are trying to find is the orientation of the satellite. Just like humans rely on senses to understand the world around them, satellites use spatialized senses to figure out where they're pointing. Like human using eyes, the sensors satellite uses are star tracker, sun sensor, or gyroscope. Star tracker, like human eye, has a camera that detects the position of the stars. Sun sensor finds the direction of the sun. Earth sensor detects the direction of the Earth. Gyroscope measures how fast the satellite is rotating, and the magnetometer senses the Earth's magnetic field like digital compass. But what do these individual measurements actually tell us? Do they directly give us orientation? The answer is no. We can think of each sensor measurement as a snapshot, an image of the sun, a star, the earth below, the strength of magnetic fields, or an arrow pointing towards the sun or the earth. On their own, these measurements only tell us what the satellite is seeing, not how it's oriented in the space. To truly understand the satellite's orientation, its precise rotation and direction in three dimensions, we need to process these observations using advanced mathematical algorithms. One of such algorithms is ESOQ-2, which takes the raw sensor data and calculates exact attitude of the satellite. Without this step, the satellite would have the data but no context. Algorithms like ESOQ-2 turns those sensor snapshots into full understanding of where the satellite is pointing. This leads us to the fundamental challenge in satellite navigation called Wahba's problem. In the early days of spaceflight, most satellites didn't even need to know where they're pointing. They simply orbited the Earth, performing basic tasks like transmitting radio signals or collecting simple data. To stay stable in space, some satellites use a technique called spin stabilization, spinning like a top to maintain a steady orientation relative to themselves. Others use a passive technique called gravity gradient stabilization. By taking advantage of difference in Earth's gravitational pull on different parts of the satellite, they would naturally align one end towards the Earth, like a pendulum hanging in space. As technology progressed, satellites began to carry basic sensors like sun sensors to detect the direction of sunlight, Earth horizon sensors to locate the edge of the Earth, and magnetometers to sense Earth's magnetic field. With these sensors, satellites could now sense their orientation relative to known celestial or terrestrial directions. It's important to note that just having vector measurement on board the satellite isn't enough. Think of it like this. If you're navigating and know that a landmark is to your right, that information alone doesn't tell your exact direction. You also need to know where the landmark is in the map to use it for orientation. Similarly, for satellites, we not only need the measured vector in satellite's frame, but also need to know what the vector looks like in the reference frame we are using to determine the satellite's orientation. Only by comparing both, we can accurately compute attitude. These reference vectors are computed using mathematical models implemented on board the satellite. To make sense of this data, engineers use simple geometric techniques like triad method, which could estimate the satellite's orientation using just two sensor measurements, for example, the direction of the sun and the Earth's magnetic field. But there were limitations. These early methods could only handle two measurements at a time, struggled with noisy data, and didn't run in real time on board the satellite. Computations were often done on the ground and the results were sent back to space. In the year 1965, Chris Wahba formulated a problem now popularly known as Wahba's problem or Wahba's optimization problem. Wahba's original publication of the paper is so concise that I could not resist from quoting it. A least squares estimate of satellite altitude by Grace Wahba in 1965 mentions given two sets of endpoints r vector and y vector where n is greater than or equal to 2, find the rotation matrix Q that is the orthogonal matrix with determinant plus 1 which brings the first set into the best least squares coincidence with the second. That is, find Q which minimizes the cost function. This problem has arisen in the estimation of the attitude of a satellite by using directed cosines yk vectors of objects as observed in the satellite fixed frame of reference and direction cosines rk vector of the same objects in known frame of reference. Q is then a least square estimate of the rotation matrix which carries the known frame of reference into the satellite frame of reference. To put it in simple terms, given a set of vector observation from the body frame and a corresponding known vector in inertial frame, we are to find the rotation that best aligns the measured vector to their reference. Mathematically, we're looking for a rotation matrix, the one that minimizes the error between the measured vector and the reference vector. This is essentially a least squares optimization problem. We want to find the rotation that brings the observed vectors into the best possible alignment with their known counterparts. After Chris Wahba first formulated the problem, researchers like Davenport and Markley were among the earliest to tackle it. They discovered that the key to the solution was finding the eigenvector associated with the largest eigenvalue of 4 into 4 symmetric matrix K. This eigenvector would be the optimal quaternion output. But back then, these computations were demanding for the onboard computer available. Because of this challenge, a whole series of algorithms sprang up, each aiming to be faster and more efficient than the last. Names like Quest, ESOQ, and ESOQ-2 emerged, each pushing the boundaries to outperform its predecessors in computation, speed, and accuracy. We chose ESOQ-2 as the paper ESOQ-2 Single-point algorithm for fast optimal spacecraft attitude determination by Professor Daniele Mortari claims this algorithm is optimal because it fully compiles with Wahba's optimality attitude definition, non-singular, thanks to the use of sequential rotation and the fastest available algorithm. Using the tools from our ADCS library, we validated the implementation of ESOQ-2 by generating synthetic noisy vector measurements and corresponding reference vectors using known quaternion profile. This quaternion profile acts as our ground truth. Then we feed the pair of vector measurements to ESOQ-2 expecting the output quaternion to be close to the ground truth. The result, as can be seen from the plot, is pretty close to the ground truth.